Right now, you probably believe the Andromeda Galaxy is 2.5 million light years away from where you are. You also likely think the closest star to us is about 4 light years away. You trust that distance in space is a real thing that can be measured and that is fixed and absolute. But what if every single measurement ever made of cosmic distances is fundamentally incorrect? What if distance itself is not a basic building block of reality, but rather an illusion created by your brain? What if, at the most fundamental level of physics, space does not contain any distance at all? What I am about to explain will permanently change how you understand the nature of space itself. Distance appears to be the most straightforward concept in existence. You are sitting some distance from the screen you are looking at right now. The moon is roughly 250,000 miles away. The sun is about 93 million miles from us. All these distances feel real, fixed, and permanent. Distance is simply how much space exists between two things. It seems like the easiest idea in all of physics, but simplicity often hides the most profound mysteries. And distance, this seemingly obvious property of space, turns out to be one of the most misunderstood ideas in all of science. Distance in space is not what your intuition tells you. It is not a fundamental feature. It is not absolute. It is not even real in the way you naturally assume it is. The path to understanding this will take us through quantum mechanics, general relativity, holography, and the very core of what space itself actually is. Let me start with something you might think you already understand: the speed of light and what it reveals about distance. When scientists say Andromeda is 2.5 million light years away, they are making a claim that sounds like a pure distance measurement, but in reality, it is a time measurement. A light year is simply the distance light covers in 1 year. So saying something is 2.5 million light years away means light takes 2.5 million years to go from there to here. But here is the issue. You are not measuring where Andromeda is right at this instant. You are measuring where it was 2.5 million years ago when that light first set out. By the time that light reaches your telescope, Andromeda has shifted its position. It has been moving for all those 2.5 million years. The distance you measure is the distance to a ghost, to where Andromeda was millions of years in the past, not to its actual location at this very moment. And because the universe is expanding, the true current distance to Andromeda is different from the distance the light had to travel to get to you. Space itself grew during the 2.5 million years the light was journeying. So the distance the light traveled is not the same as the distance between you and Andromeda right now. Every measurement of cosmological distance mixes up at least 3 separate distance concepts: the distance the light actually traveled, the distance at the time the light was emitted, and the present distance that accounts for cosmic expansion. All of these numbers are different. Which one is the genuine distance? The answer is that none of them is more real than any other. They are all valid ways to describe separation, depending on the question you are asking and the reference frame you are using. There is no single true fact about how far away a distant galaxy really is. Right now, distance on a cosmic scale is dependent on the observer and on the definition being used. It is not an absolute truth about the universe. But this is only the starting point. Special relativity goes much further in destroying any notion of absolute distance. In 1905, Einstein demonstrated that distance is relative. Not just approximately relative or sort of relative, but absolutely and fundamentally mathematically relative in a way that depends on your speed. Here is the key result. A ruler moving past you at high velocity is shorter than the exact same ruler when it is at rest. Not because the ruler is physically squeezed, not because anything is pushing on it, but because the geometry of space-time is such that a moving object takes up less space in its direction of motion compared to when it is stationary. This is called length contraction, and it is a real effect that has been confirmed by experiments. At 10% of light speed, an object contracts by roughly 0.5% in the direction it is moving. This is small, but can be measured. At 90% of light speed, it contracts to about 44% of its length when at rest. At 99% of light speed, it contracts to about 14% of its resting length. As you get closer to light speed, the length approaches zero. What does this mean for distances across the cosmos? It means that distance depends on your frame of reference. If you are on a spaceship traveling at 99% of light speed toward Andromeda, the distance from you to Andromeda is not 2.5 million light years. It is 2.5 million light years divided by the Lorentz factor, which at 99% light speed gives you a distance of about 350,000 light years. You and someone standing still on Earth would measure completely different distances to that same galaxy. Both measurements are entirely correct within their own reference frames. There is no absolute distance, even at the speed of light. From the perspective of a photon, the contracted distance would be zero. We have already discussed in a previous video that a photon does not really have a perspective. But if it did, the distance from where it started to where it ends up would be exactly zero. The whole observable universe has zero size from the reference frame of light itself. So distance in space is already not absolute. It relies on your speed. It relies on your frame of reference. Different observers get different distances between the same 2 points, and all of their measurements are equally valid. There is no real fact about the true distance between 2 points in space that exists independently of who is measuring it and how they are moving. But even this is not the deepest level where distance breaks down. General relativity goes even further. In general relativity, space itself is curved. Mass and energy bend the shape of space-time. Near a heavy object, space becomes significantly warped. This means the distance between 2 points is not set by some unchanging background geometry. It is instead set by the arrangement of matter and energy between and around those points. Near a black hole, space is so extremely curved that the distance from outside the event horizon to the singularity within is effectively infinite. Even though the black hole has a finite radius when measured from outside, an observer falling inward experiences the interior of the black hole as having an enormous volume, far larger than what the black hole appears to be from the outside. The inside of a black hole contains a vast amount of space that cannot be accessed from the outside. This shows that distance is not a fixed property of space. It is set by the geometry, which is itself set by matter and energy. Change how matter and energy are distributed, and you change all the distances throughout the universe. Distance is not a passive background where physics takes place. It is itself a physical quantity that shifts depending on the physical state of the universe. Curved space also means that the shortest route between 2 points is not a straight line. In curved space-time, the shortest paths are called geodesics, and they follow the curve of space. The distance along a geodesic depends on the curvature, and the curvature depends on how mass and energy are spread out. 2 points that are close together in flat space might be far apart along the geodesic if a massive object sits between them. They might also appear close together due to gravitational lensing, where light bends around a massive object. Even the idea of 2 points being in the same location becomes strange inside a black hole due to the extreme warping of space-time. 2 points that are at the same spatial location according to one coordinate system can be at very different locations according to another coordinate system. The coordinates we use to label positions in space-time are not fixed. Different choices of coordinates give completely different pictures of which points are near each other and which are far apart. This is not just a technical mathematical detail. Physical effects actually depend on the coordinate choice. What appears as a strong gravitational field in one coordinate system can look like flat, empty space in another. What looks like a huge distance in one set of coordinates can appear as a tiny distance in another. The facts about space-time that do not depend on coordinates are about its overall geometry and shape, not about simple distances between individual points. Now we arrive at the deepest and most radical way in which distance in space is an illusion: quantum entanglement and the holographic principle. Quantum entanglement is perhaps the most bizarre phenomenon in all of physics. When two particles interact and become entangled, they form a single quantum system described by one wave function, no matter how far apart they are later moved. If you measure a property of one particle, you instantly know the matching property of the other particle, regardless of the gap between them. Einstein called this spooky action at a distance and spent many years trying to show it was impossible. He was mistaken. We have verified entanglement in thousands of experiments. Two entangled particles could be on opposite edges of the observable universe, and they still remain one quantum system. Being separated in space does not break entanglement. Distance does not weaken it. Two entangled particles that are billions of light years apart are quantum mechanically closer to each other than two unentangled particles that are physically touching. This reveals something extremely deep. Quantum mechanical closeness and spatial closeness are completely separate things. Two particles can be far apart in space but strongly connected at the quantum level. Two particles can be right next to each other but quantum mechanically independent. Spatial distance does not capture what is truly happening at the level of quantum reality. Physicist Juan Maldacena made one of the most groundbreaking discoveries in the history of theoretical physics. In 1997, he found a precise mathematical connection called the AD-S/CFT correspondence between a theory of gravity in a certain curved space-time and a quantum field theory without gravity that lives on the boundary of that space-time. The gravity theory exists in a space with one extra dimension compared to the boundary quantum theory. Yet both descriptions are exactly equivalent. Every measurable thing in one theory has a direct match in the other theory. They describe the exact same physical reality from two completely different viewpoints. This is the holographic principle in its most exact mathematical form. The physical reality we experience in three dimensions of space can be completely and accurately described by a theory that lives on the two-dimensional boundary of that space. The third dimension of depth, the dimension that gives us our sense of volume and distance, is not fundamental. It comes into being from the quantum entanglement structure of the boundary theory. Think about what this means for distance. In the three-dimensional bulk theory, you have distances. Things are near or far. Gravitational effects depend on distance. The geometry of space-time sets all these distances. All of this appears fundamental and real. But in the two-dimensional boundary theory, there is no such bulk distance. The boundary theory has its own two-dimensional distances and geometry. But the three-dimensional depth, the distance going into the bulk, is not a geometric distance in the boundary theory. It corresponds to something entirely different. In fact, it corresponds to the energy scale of the boundary theory. High energy processes in the boundary theory match to small distances from the boundary and the bulk. Low energy processes match to large distances from the boundary. What we experience as distance in the third dimension of space is actually a measure of energy scale. In the underlying quantum theory, distance is not fundamental. It is a way of describing quantum mechanical connections between degrees of freedom at different energy levels. Depth in space is an emergent property that comes from the structure of quantum entanglement in the boundary theory. This is not a rough estimate or a loose analogy. This is an exact mathematical equivalence that has been proven to a very high degree of precision. Space, specifically the radial distance dimension in this holographic picture, is quite literally built from quantum entanglement. Recent work by physicists Mark van Ramsdonk, Brian Swingle, and others has made this link even clearer. They have shown that the geometry of space-time, including all its distances and curvatures, is shaped by the entanglement structure of the underlying quantum fields. In particular, a concept called entanglement entropy, which measures how quantum mechanically linked different parts of a quantum system are, determines the geometry of the corresponding space-time. Regions of space-time that are close together match to strongly entangled regions in the quantum description. Regions of space-time that are far apart match to weakly entangled regions. Distance in space is entanglement in quantum mechanics. These are two ways of describing the same underlying reality. Van Ramsdonk illustrated this with a beautiful thought experiment. Take the quantum state of the boundary theory and reduce the entanglement between two halves of it. What occurs in the bulk space-time? The bulk space-time splits into two disconnected pieces. As you keep reducing the entanglement, continue until it reaches zero and the two halves of the bulk space-time become fully disconnected with an infinite gap between them. Restore the entanglement and the two halves reconnect and the distance shrinks. Space-time connectivity, the fact that different areas of space are linked to each other with finite distances, is literally generated by quantum entanglement. Remove entanglement and space falls apart. Add entanglement and space is woven together. Distance is not a property that space has on its own. Distance is a manifestation of quantum entanglement between the pieces that make up space. This insight has led to one of the most exciting recent developments in theoretical physics. The ER equals EPR conjecture, proposed by Maldacena and Leonard Susskind. Einstein-Rosen bridges, which are wormholes linking two distant parts of space-time, are named after Einstein and Rosen, who first described them mathematically. Einstein-Podolsky-Rosen pairs, which are maximally entangled quantum particles, are denoted EPR after the famous 1935 paper by Einstein, Podolsky, and Rosen. The conjecture states that ER equals EPR, meaning an Einstein-Rosen bridge connecting two black holes is the same as an EPR entanglement between those two black holes. A wormhole joining two distant regions of space is equivalent to maximum quantum entanglement between those regions. The geometric connection through a wormhole and the quantum mechanical connection through entanglement are the same thing described in two different languages. What does this mean? It means that entangled particles are joined by a kind of quantum wormhole, a geometric bridge through space-time created by their entanglement. Two particles that appear to be spatially far apart from each other because you cannot see the quantum bridge between them are in fact geometrically linked through that bridge. The distance between them is an illusion created by looking at the wrong level of description. Our everyday idea of distance, the distance you measure with a ruler or a laser rangefinder, is the large-scale emergent picture. Underneath it, at the quantum level, the real structure is entanglement. Two entangled particles are not distant from each other in any fundamental sense. They are connected. Distance is a large-scale illusion that appears when you average over quantum details. Loop quantum gravity provides yet another angle on why distance is not fundamental. In loop quantum gravity, space-time is not smooth and continuous at tiny scales. Instead, it is made of discrete quantum pieces, small chunks of space called spin networks. The nodes of a spin network represent quanta of volume. The links between nodes represent quanta of area. Distances in loop quantum gravity are not continuous amounts. They are discrete steps that come in minimum units related to the Planck length, which is about 10 to the minus 35 meters. At scales smaller than the Planck length, the idea of distance becomes meaningless. Not just impossible to measure, but truly meaningless. There is no physical fact about whether two things are separated by less than a Planck length, because spatial separation below that scale is not a valid concept. Space is not infinitely divisible. It has a smallest unit, and below that unit, the entire idea of distance falls apart. This means that our smooth, continuous space with its infinitely precise distances is an approximation. It works very well at scales much larger than the Planck length, but it is not the fundamental reality. Fundamental reality is a discrete quantum network where classical distance arises as a large-scale statistical property of the network. The same way temperature arises from the average motion of molecules, even though individual molecules do not have a temperature. Distance in space is therefore doubly misleading. At the quantum gravity scale, space is discrete and distance loses its classical meaning entirely. At larger scales, distance emerges as an approximate description of the underlying quantum network structure. But this emergence means distance is not fundamental. It is something that comes from something else. The implications of all this are astonishing. Two galaxies that appear separated by millions of light years might be connected by quantum entanglement in ways that make that spatial distance physically irrelevant for quantum processes. The apparently enormous gaps between stars might be, at the quantum level, descriptions of entanglement structures rather than fundamental empty space. The universe that seems to stretch across billions of light years might be, at its deepest level, a quantum system where what matters is not spatial geometry but quantum connectivity. This does not mean you can instantly teleport across the galaxy by using quantum entanglement. Entanglement does not allow faster-than-light communication or movement of matter. The quantum link between entangled particles does not create a passable tunnel for information or energy. The distance is illusory at the fundamental level, but the limits on what can physically happen between distant regions remain in place. You cannot use the underlying quantum connectivity to break causality. But it does mean that our whole picture of the cosmos as a huge empty space with things spread out across enormous distances is deeply misleading. The universe is not primarily a spatial structure. It is primarily a quantum structure. The spatial distances we observe are a large-scale emergent description of the quantum entanglement architecture of reality. Think about what this means for how you see the night sky. When you look up and see the Milky Way stretching across the dark with stars at distances of hundreds and thousands of light years, you are not seeing fundamental gaps in space. You are seeing the large-scale average of a quantum entanglement network. The apparent distances are real as large-scale descriptions, but they are not the bottom layer of reality. When you look at the Andromeda Galaxy and consider the 2.5 million light-year gap between us and it, remember that this distance is dependent on your frame of reference, on your motion, on your definition, and ultimately emerges from quantum entanglement structures that do not themselves operate in terms of spatial distance. When cosmologists measure the size of the observable universe as 93 billion light years and call it unimaginably vast, remember that this vastness is a description in the approximate language of classical geometry. In the underlying quantum description, there are no 93 billion light years. There are quantum states and their entanglement patterns, and the geometry, including all those distances, emerges from those patterns. Distance in space is real in the same way temperature is real. You can measure it. You can sense it. You can build technology based on it. But it is not fundamental the way quantum states are fundamental. It is an emergent, approximate, observer-dependent description of something deeper that has no distances at all. The universe is not a collection of objects spread across a huge space. The universe is a quantum system. And what we call space, with all its distances and shapes, is how that quantum system appears from the inside. When you are a large being made of trillions of atoms interacting at energies far above the quantum gravity scale, You are not separated from the stars by light years. You are linked to them through a web of quantum entanglement, whose large-scale description we call space. Every particle in your body is quantum mechanically connected to particles throughout the cosmos. The apparent distances between you and everything else are the large-scale shadow of quantum connections that have no spatial description at the fundamental level. This is what distance in space truly is. Not a fundamental property of reality, not an absolute fact about how far things are from each other, but an emergent, approximate, observer-dependent description of quantum entanglement architecture. A useful fiction that we mistake for fundamental reality because we are too large to see the quantum structure beneath. The universe is not vast. The universe is quantum. And in the quantum description, there are no distances.